Yeah, welcome back, friends. Yeah, we are today uploading part 3 of the missing videos. As you know, 4 of the starting videos are missing from our channel page. So, the first 2 parts I already uploaded. Today I am uploading Java programming part 3 of 33. There's only one more to be uploaded, which I will do it the next day. So this is also, as I explained earlier, very much in the area of theory and explanation of the language. We are actually still not started programming parts, programming section. We are still, this is the last of that section of explanation part. We are still investigating the features of the Java language. This is actually the last. Next one is actually the scenario of the installation process. The installation process of the Java software and the associated development environment. So for integrated development environment like ID, in our case we are using Eclipse. Okay, that and all that I will explain in the next video. So here is again, we will just go through the buzzwords of Java, the so-called buzzwords of Java. See, they say it is simple, quite simple, secure, portable, object-oriented, robust, multi-threaded, interpreted, distributed, high performance, and dynamic in nature. So, these are the Java buzzwords. These are the Java buzzwords. See, it's robust, multi-threaded, interpreted, distributed, dynamic, high performance, etc. Fine. You know, I think you are very much familiar with these concepts. And another important aspect is we are now coming with the so-called object-oriented features of the language. Almost all of you might be knowing the object-oriented basics. See, it is like encapsulation, concepts like encapsulation, inheritance, and polymorphism, etc., are explained in detail towards the end of this video. So this video also, as I said, is pertaining to the explanation part of the Java language. The next video onwards, we will come with the proper installation process and subsequent programmings. Okay, now this is very much you should look into with seriousness, because don't skip it, because it's all very important to see that you are understanding the basics of the language in great detail, because that will give you a greater appreciation of the Java language. Why it is still popular, that is a major aspect. Why Java is still very much popular in spite of the fact that there are so many other languages on earth. Java is still very, very popular. Fine, I think it's good. We will just stop this talk and we will go into the details of the video. Yeah, part 2, the Java buzzwords. The Java buzzwords. Let us have a look at the ever famous Java buzzwords now. Although the fundamental forces that necessitated the invention of Java are portability and security, other factors also played an important role in modeling the final form of the language. Those key considerations were summed up by the Java team in the following list of buzzwords. Following are those buzzwords. We will look at it. Fine. list of buzzwords. We are now listing those buzzwords. Look. See, simple, next secure, next portable, next object oriented, next robust, next multi-threaded, next interpreted, then high performance, and distributed, finally dynamic. Look, these are the buzzwords. Once again I will tell it. Simple, secure, portable, object-oriented, robust, multi-threaded, interpreted, high performance, distributed, and dynamic. Two of these buzzwords we already discussed in detail, secure and portable. Let us look at the rest. Let us look at the rest. Simple. Look, we are going one by one. Look, simple. Java was designed to be easy for the professional programmer to learn and use effectively. Assuming that you have some fundamental programming experience, you will not find Java hard to master. Next, if you are an experienced C++ programmer, moving on to Java is effortless because Java inherits the C/C++ syntax and many of the OOPS principles followed in C++, most programmers have little trouble learning Java. Object oriented. Look, Java is object oriented. Fine. Unlike C++, Java was not graduating to an object oriented paradigm from a procedure oriented setup, but started life as object oriented from the very outset. This allowed the Java team the freedom to design from a blank slate. Next. One outcome of this was a clean, pragmatic approach to objects. Borrowing liberally from many seminal object software environments of the last few decades, Java manages to strike a balance between the hardcore theory and what should work out in practice. The object model in Java is simple and easy to extend, while primitive data types like integers are kept as high performance non-objects. Next, robust. The multi-platformed environment of the web places extraordinary demands on a program, because the program must execute reliably in a variety of systems, full stop. Thus, the ability to create robust programs were given a high priority in the design of Java. To better understand how Java is robust, consider two of the main reasons for program failure. See, memory management mistakes and mishandled exceptional conditions. Full stop. Java virtually surmounts this problem by managing memory allocation and deallocation for you. In fact, deallocation is completely automatic, because Java provides a mechanism called garbage collection, which takes care of cleaning unused objects. Also, Java provides object-oriented exception handling to deal with exceptions that occur in your program in a structured and systematic manner. Great. Next, multi-threaded. See, Java was designed to meet the real world requirement of creating interactive, networked programs. To accomplish this, Java supports multi-threaded programming, which allows you to write programs that do many things simultaneously. Now look, The Java runtime system comes with an elegant and sophisticated solution for multi-process synchronization that enables you to construct smoothly running interactive systems. Java's easy-to-use approach to multi-threading allows you to think about the specific behavior of your program, not the multi-threading subsystem. See, to use Java's easy-to-use approach to multi-threading allows you to think about the specific behavior of your program, not the multi-threading subsystem. That's it. Yeah, architecture neutral. Look, we are discussing the point architecture neutral. A central issue for the Java designers was that of code longevity and portability. At the time of Java's creation, one of the main problems facing programmers was that no guarantee existed that if you wrote a program today, it would run tomorrow, even on the same machine. Even on the same machine. Look. Next, operating system updates, and changes in the core system resources can all combine to make a program malfunction. The Java designers made several hard decisions in the Java language and the Java virtual machine in an attempt to alter this situation. Their goal was write once, run anywhere, anytime, forever. Their goal was write once, run anywhere, anytime, forever. See, to a great extent, this goal was accomplished. Great. Interpreted and high performance. As described earlier, Java enables the creation of cross-platform programs by compiling into an intermediate representation called Java bytecode. This code can be executed on any system that implements the Java virtual machine. Next, most previous attempts to accomplish cross-platform solutions have done so at the expense of performance. As explained earlier, the Java bytecode was carefully designed so that it would be easy to translate directly into native machine code for very high performance by using a just-in-time compiler. Java runtime systems that provide this feature lose none of the benefit of the platform independent code. That's it. Next is distributed. The next concept is distributed. Look, Java is designed for the distributed environment of the internet because it handles TCP/IP protocols. In fact, accessing a resource using a URL is not much different from accessing a file. Full stop. Java also supports what is called remote method invocation, in bracket RMI, remote method invocation. Full stop. This feature enables a program to invoke methods across a network. See, next point is dynamic. Java programs carry with them substantial amount of runtime type information that is used to verify and resolve access to objects at runtime. Full stop. This makes it possible to dynamically link code in a safe and expedient manner. This is crucial to the robustness of the Java environment, in which small fragments of bytecode may be dynamically updated on a running system. Fine. Yeah, the different versions of Java different versions of Java. Look, the initial release of Java was nothing short of revolutionary, comma, but it did not mark the end of Java's era of rapid innovation, full stop. Unlike most other software systems, comma, that usually settle into a pattern of small incremental improvements, comma, Java continued to evolve at an explosive pace. At an explosive pace. Soon after the release of Java 1.0, the designers of Java had already created Java 1.1. Full stop. The next major release of Java was Java 2, meaning second generation Java. Java 2 added support for a number of new features such as swing and the collection framework. J2SE, that is Java 2 Standard Edition 1.3, J2SE 1.3, was the first major upgrade to the original release, to the original Java 2 release. The release of J2SE 1.4, Java 2 Standard Edition 1.4, J2SE 1.4 further enhanced Java. This release contained several important upgrades, enhancements, and additions. Fine. Yeah, subsequent Java versions. Look, the next release of Java was Java 2 Standard Edition 5, J2SE 5, and it was revolutionary. It was revolutionary. Unlike most of the previous Java upgrades, comma, which offered important but measured improvements, comma, Java 2 SE5, J2 SE5 fundamentally expanded the scope, comma, power and range of the language. To grasp the magnitude of changes that J2 SE5 brought to Java, consider the following list of major new features. The list of major new features. Look, generics, next annotations, next auto boxing and auto unboxing, then enumerations, then enhanced for each style for loop, for each style for loop, variable length arguments, var args, static import, formatted input output IO, concurrency utilities, concurrency utilities. Then came Java Standard Edition 6. After that, Java Standard Edition 7 appeared. Java SE7 was the first major release of Java since Sun Microsystem was acquired by Oracle Corporation. Since Sun Microsystem was acquired by Oracle Corporation. Fine. Java SE7, that is Java Standard Edition 7, contained many new features, including significant addition to the language and the API libraries. The new language features were developed as part of what is called Project Coin. Project Coin was to identify a number of small changes to the Java language that would be incorporated into JDK 7. The next release of Java was Java SE8, that is Java Standard Edition 8, with the developers kit being called as JDK 8. With the developers kit being called as JDK 8. And JDK 8 was a significant upgrade to the Java language because of the inclusion of a far-reaching new language feature called the lambda expression. The impact of lambda expression was, and will continue to be, profound, changing both the way that programming solutions are conceptualized and how Java code is written. It's a revolutionary change, look, and it will continue to be profound, changing both the way that programming solutions are conceptualized and how Java code is written. See, that's the power of the lambda expression. Fine. Java SC9, Java Standard Edition 9. Fine. The newest release of Java is Java SC9, Java Standard Edition 9, Java SC9. The developer's kit is called JDK 9. With the release of JDK 9, the internal version number is also 9. JDK 9 represents a major Java release, incorporating significant enhancements to both the Java language and its libraries. Like JDK 5 and JDK 8 releases, JDK 9 affects the Java language and its API libraries in fundamental ways. Fine. Object-oriented programming and Java. Object-oriented programming and Java. Look. Object-oriented programming is at the core of Java. Full stop. As we already mentioned, Java started life as object-oriented from the very outset, quite unlike C++, which was redesigned into it. Hence, in this chapter, we discuss the theoretical foundations of OOPS in some detail. Let us discuss it. See it. Two paradigms. Look. All computer programs consist of two elements. I have put a colon here. Look. Code and data. What is it? Code and data. Furthermore, a program can be conceptually organized around its code or around its data. That is, some programs are written around what is happening. See, I have put what is happening with a double quote. Some programs are written around what is happening, and others can be written around who is being affected. Look, I have put who is being affected with a double quote. Who is being affected, full stop. These are the two paradigms that govern how a program can be constructed. The first way is called process-oriented model. It's also called procedure-oriented or function-oriented. This approach characterizes a program as a series of linear steps. The process-oriented model can be thought of as functions acting on data. Procedure languages such as C and Pascal employ this model to considerable success. Moreover, as we already discussed, problems with this approach begin to creep as programs grow in size and complexity. When programs grow in size and complexity, problems creep. Problems began to appear. Look, see. To manage increasing complexity, the second approach called object-oriented programming was conceived. Object-oriented programming organizes a program around its data, that is objects, and a set of well-defined interfaces to that object. Abstraction. We are discussing the point of abstraction. An essential element of object-oriented programming is abstraction. Humans manage complexity through abstraction. For example, people do not think of a car as a set of tens of thousands of individual parts. They think of it as a well-defined object with its own unique behavior. This abstraction allows people to use a car to drive them up. They simply ignore the details of how the engine, transmission, and the braking system work. Instead, they are free to utilize the object as a whole. They are just utilizing the object as a whole. Look. Next. A powerful way to manage abstraction is through the use of hierarchical classifications. This allows you to layer the semantics of complex systems, breaking them into more manageable pieces. Hierarchical abstractions of complex systems can also be applied to computer programs. The data from a traditional process-oriented program can be transformed by abstraction into its component objects. A sequence of process steps can become a collection of messages between these objects. Thus, each of these objects describes its own unique behavior. You can treat these objects as concrete entities that respond its messages, telling them to do something. To messages telling them to do something. This is the essence of object-oriented programming. This is the essence of object-oriented programming. Yeah, abstraction continued. We are continuing our discussions on abstraction. Look, object-oriented concepts form the heart of Java as they form the basis for human understanding. It's important that you understand how these concepts translate into programs. As you will see, object-oriented programming is a powerful and natural paradigm for creating programs that survive the inevitable changes accompanying the life cycle of any major software project, including conception, growth and aging, full stop. For example, once you have well-defined objects and clean, reliable interfaces to those objects, you can gracefully decommission or replace parts of an older system without fear. Fine. Yeah, the three OOPS principles. The three OOPS principles. Look, all object-oriented programming languages provide mechanisms that help you implement the object-oriented model. They are encapsulation, inheritance, and polymorphism. Let us take a closer look at these concepts now. See the first one. Let us see encapsulation. You know, it's encapsulation, inheritance, and polymorphism. We now discuss what is encapsulation. Look, encapsulation is the mechanism that binds together code, in brackets simply the functions, and the data it manipulates. That binds together functions and the data it manipulates, and keeps both safe from outside interferences and misuse. One way to think about encapsulation is as a protective wrapper that prevents the functions and data from being arbitrarily accessed by other functions outside. So other functions defined outside the wrapper. The power of encapsulated code is that everyone knows how to access it and thus can use it regardless of the implementation details and without fear of unexpected side effects. Without the fear of unexpected side effects. Fine. Encapsulation. In Java, the basis of encapsulation is the class. A class defines the structure and behavior of data and functions that will be shared by a set of objects. Each object of a given class contains the structure and behavior defined by the class. For this reason, objects are referred to as instances of a class. Thus, a class is a logical construct, and an object is a physical entity. Fine. An object is a physical entity while a class is a logical construct. Fine. When you create a class, you will specify the functions and data that constitute that class. Collectively, these elements are called members of the class. Specifically, the data defined by the class are referred to as member variables or instance variables. The functions that operate on that data is referred to member functions or just methods. In properly written Java programs, the methods define how the member variables can be manipulated. This means that the behavior and interface of a class are defined by the methods that operate on its instance variables. That's fine. Yeah, encapsulation continued. Since the purpose of a class is to encapsulate complexity, there are mechanisms for hiding the complexity of the implementation inside the class. Each method or variable in a class may be marked as private or public. So it can be marked as private or public. The public interface of a class represents everything that external users of the class need to know or may know, full stop. Normally, data will be declared as private, and private data can only be accessed by functions / methods that's a member of the class. That's a member of the class. Fine. Yeah, inheritance. We are now discussing the concept of inheritance. Inheritance is the process by which one object acquires the properties of another object. One object acquires the properties of another object. This is important because it supports the concept of hierarchical classification. As mentioned earlier, most knowledge is made manageable by hierarchical, that is top-down classification. For example, a golden retriever is part of the classification dog, which in turn is part of the mammal class, which is again under the large class animal, under the larger class animal. Fine. Now next, without the use of hierarchies, each object would need to define all of its characteristics explicitly. However, by the use of inheritance, an object needs only define those qualities that make it unique within its class. It can inherit its general attributes from its parents. Thus, it is the inheritance mechanism that makes it possible for one object to be a specific instance of a more general one. A more general one. Fine. Most people naturally view the world as made up of objects that are related to each other in a hierarchical way, such as animals, mammals and dogs. if you were to describe a more specific class of animals, such as mammals, they would have more specific attributes such as type of teeth, and mammary glands, etc. Full stop. Thus, so sorry, this is known as a subclass of animals, where animals are referred to as mammals superclass. Fine. Mammals superclass. Fine. The concept of subclass and superclass is mentioned here. Fine. Yeah, inheritance continued. We are continuing our discussions on inheritance. Since mammals are simply more precisely specified animals, they inherit all the attributes from animals. Full stop. A deeply inherited subclass inherits all of the attributes from each of its ancestors in the class hierarchy. Fine. Next. Inheritance interacts with encapsulation as well. Full stop. If a given class encapsulates some attributes, then any subclass will have the same attributes plus any that it adds as part of its specialization. Full stop. This is the key concept that lets object-oriented programs grow in complexity linearly rather than geometrically. They grow in complexity linearly rather than geometrically. A new subclass inherits all of the attributes of all its ancestors. Of all its ancestors. Yeah, now it is polymorphism. We are discussing the concept of polymorphism. Look, polymorphism, in bracket I have put, from Greek, meaning many forms, close the bracket, is a feature that allows one interface to be used for a general class of actions. One interface to be used for a general class of actions. Full stop. The specific action is determined by the exact nature of the situation. Consider a stack. Look, a stack is nothing but which is a last in first out list. A stack is nothing but which is a last in first out list. Close the bracket, full stop. You might have a program that requires three types of stacks. Three types of stacks. Look, one stack is used for integer values, one for floating point values, and one for characters. The algorithm that implements each stack is the same, even though the data being stored differs. In a non-object oriented language, you would be required to create three different set of stack routines, with each set using different names. However, because of polymorphism, in Java, you can specify a general set of routines that all share the same name. Fine.